thanks first of all for being invited to speak here today, and apologies to those who heard me speak yesterday because it's not going to be all that different. But there is a prize if you can find the 3 slides that I've changed since yesterday. You'll see that this is a talk about making 3D geological models, and to back me up I've got probably the 2 people who have made the most regional scale 3D geological models in their respective countries. It's Laurent, who's at Monash University but also a consultant, and Kemp, who's with the Geological Survey of Canada. And so when we slag off geological models, at least they know what we're talking about. So what I'm going to do is, first of all, give you a couple of ads. There's, for those of you that are real 3D junkies and haven't had enough geophysics this week, there's going to be 2 talks by 2 of the gurus of geophysical inversion at CET tomorrow. Anybody can turn up, it's no cost, just find the right room. And also later on in the year, we're having a conference at Margaret River on, with a great lineup of speakers that if you want more information, go to the CET website and look in news and events. But I'm going to show you a slide that you've probably seen at least 10 times this week, the slide of time versus depth of discovery of different deposits. And with the inference is that we're having to look deeper and deeper. We've already had talk on the uncover, so I won't go through that logic again. But the result of this logic is that, for example, in Australia, a great many 3D geological models have been made at the regional scale. Of course, all these black dots are active mines, and they also have a 3D geological model. And that in itself raises the question of how do we go from these sort of essentially detailed point 3D geological models to the regional ones. It's the same question as how do we go from a drill hole to extrapolating what's going on around a mine. It's a multi-scale problem, and I have no answers for how we do that. If you look at geophysical inversion, there's unconstrained inversions where we just take the pure field that we've measured and we put in some boundary conditions, and we can get a nice inversion like this. There's geologically constrained ones where we put in the starting geological geometry, and there's petrophysically constrained ones where we put in the geometry and the detailed variations in the petrophysics in order to understand how these things are changing. These slides are out of order, so I'll ignore them. So just as there are different types of geophysical inversion, there are different types of geological modeling, and I'm not going to go through them in detail here, except to say that really for what I'm going to talk about for the rest of the talk, I'm going to be talking about using implicit geological modeling schemes. And what I mean by that is that we put in the geological observations, we put in a series of less direct inferences about the geology. So a direct observation would be, I've seen this rock type, I've seen this fault. A less direct observation would be, I know that this fault is younger than that fault. So we put in both of those types of information, we press the button, and it automatically generates a 3D model. In the real world, when we do that, we go, oh, that's a terrible model, but it's the only way to go for what we're doing here. There are an awful lot of 3D modeling software packages out there, and I'm only going to be talking about, as I said, these implicit ones, and there's a whole range of different companies that do or are certainly going to, in the near future, have these implicit schemes. So I don't really care which ones I use. The examples I'm going to give use GeoModeler because they were one of the earliest ones to come up with this, so we've had the most time to work with it. When I'm talking about 3D geological models, although many of the concepts that I'm going to talk about work at these different scales, the particular scale that I'm looking at is this scale here. It's the regional scale, where we don't have these wonderful seismic data sets, we don't have these wonderful drill hole data sets, and we do have very complicated geology. So we're setting ourselves the hardest problem, and hopefully by setting ourselves the hardest problem, some of the easier problems will fall out for some of these other scales. It's the hardest because we only have gravity, we have magnetics, we don't have seismic, we have sparse seismic reflection sometimes, we have sparse MT, but we don't have the detail that we have, and the geology is horrendously complicated nearly always, at least in areas where we're looking for ore deposits. If we take the current best practice to how to make a geological 3D model, we do something where we basically start off with a blank 3D volume, and we start to add data to it, and we start to join up different surfaces to make stratigraphic surfaces or faults. And as we're going along, we have to make a whole series of decisions. We're putting in data as we go along. We might have cross-sections that we add. We might have geophysical data that we're using to constrain certain depths. And we make a whole series of decisions. And as we go down, we keep on making decisions all the way through the modeling process. And at the end, we end up with our best guess model. And you've used all of the knowledge of the geologist, you've used all of the data, and at the moment, people argue this with me all the time, is that that's the best we can do. And to be honest, at the moment, that's the best we can do, but it's not good enough. And the reasons that it's not good enough are because there's no separation of data and interpretation. So we're making these decisions all the way along, but by the end, we've got a model, but only the person that made the model has any idea what the assumptions were that went into that model. There are no error bars in this model because only the person that made the model knows which bits of the model are dodgy and which bits are solidly defined by data. It's not reproducible. Even the same geologist, if you give them the same data from scratch, will come up with a different model because going down this path is incredibly nonlinear and very difficult to reverse. So by the time you've got down here, if you suddenly decide that this decision was wrong, that's another 6 months or 4 months of work, so it's just not going to happen. And the final reason why this is a bad way of the best practice is actually terrible is that it gives you one model, and as has already been pointed out today, the uncertainty associated with all of this means that one model is not enough, and you're asking, from a geologist's point of view, you're asking the geophysicist to do all the work. We're going to give you a starting model, and then you're going to invert from that to try and find the right answer. And if you only have one model to work from, then you're asking too much of a data set like gravity or magnetics, which is fundamentally quite a weak system. So the fundamental problem is that 3D geology is hopelessly, and I mean hopelessly, under-constrained, especially at the regional scale where you have almost no drilling. So if it's under-constrained, that means that we don't really want to limit ourselves to one geological model. We want to produce 1,000 models, or maybe 1 million if we're being ambitious. But if each model takes a month to produce, then we're not going to do it. So the 3D modeling tools that we need for the future are tools where, and this goes against all of my better judgment as a geologist, is that we throw the data and we press the button and we get a model. But in fact, when you look at the 3D models that are built today, there's an awful lot of fake detail. People put in these beautiful structures because that's how they visualize them to be. But there's actually no data to constrain this beauty, so should we really be putting it in at all? I mean, it makes the geologist happy, and I'm a geologist, so I'm happy, but it doesn't actually, it's not really very scientific, and it doesn't actually lead to testable conclusions. And there are all sorts of justifications for why we shouldn't use just one model, and one of them is that there's all sorts of uncertainty associated even with the data that we collect. And I'm not going to go into detail, but obviously one of the big uncertainties results from undersampling. We sample as a geologist, we sample the top surface of the Earth, the occasional boreholes, and there are huge areas in between where we have no data. I won't go through all of these, it's not really necessary for this talk. This slide is the most important slide in trying to understand what we're trying to do. So you can forget about the rest of the talk after this. Here we have a 2D geological cross-section. And we have two faults, the red and the blue, and the bit of stratigraphy that we don't really need to worry about. And let's imagine for a moment that these faults are really key to controlling whatever it is we want to understand. In this context, it's probably mineralization. And let's say that in order to get mineralization, we have to be where these two faults intersect. It's not an unreasonable model. It's a very simple model. And of course, there's some uncertainty in what's going on here. And if we take a normal view of uncertainty, we say it's some sort of geometric uncertainty, and so we can fuzz up the positions, and that gives us an uncertainty as to where exactly we should be drilling. It's not just a point where these two things intersect, it's actually some sort of fuzzy zone around that. But if we take a geological uncertainty and say that, well, actually, you know, even though we've measured the faults at the surface, who knows what they're doing at depth, plus or minus 10 degrees seems like a reasonable estimate of the uncertainty. Maybe it's more, maybe it's less. But if we don't know, plus or minus 10 degrees on a fault doesn't seem like that much, and it's not something that gravity magnetics are going to easily be able to get you any closer than that. And as is often the case in the real world, we don't know what the relative age of these two faults is. And if we don't know what the relative age of these two faults is, and the faults can dip plus or minus 10 degrees, we end up with a situation that looks like this for possible end-member solutions. And if we end up with a situation like that with possible end-member solutions, the positions of the intersections of the two faults now looks like this. So good luck with trying to drill that on the first go. So what this tells us is that even small amounts of geological uncertainty, and in fact they're large amounts of geological uncertainty, mean that all of these models are plausible. They're not necessarily all got the same probability, but they're all plausible models, solutions to what we're looking for. And so if these are all the different solutions, then you can go, well, that's great, because now I know if I drill these two drill holes, that's the most likely I am to find the right solution, because I'm going to drill through the largest density of these possible outcomes. But the trouble is that if you happen to miss, you learn very little about the system. You learn almost nothing about the system if you don't actually hit the intersection of those two faults. If you'd have drilled the holes like this, with two holes you can actually define the entire system. So this goes a bit back to this idea of not hitting the solution on the first thing isn't such a bad idea. It's a bad idea if you're actually trying to find the target. It's not a bad idea here, because with two holes I can more or less define the entire system, and then with the third hole I'll know where to go. Once we've got 1,000 models, and I'll show you how to make 1,000, I mean here there's an example of making, I think it was 1, 2, 3, 4, it was 8 different models here. But if you can make 8 models, you can make 1,000 models. And if you can make 1,000 models, then you can start to look at what do I know and what do I not, what don't I know. And for example here, we've plotted up in a very simple Graben model a whole series of different possible solutions by varying our assumptions, and we can get an idea of what the range where that surface might be. And we can see, not only can we see what the range is, but we can see that the uncertainty associated with the position of the blue horizon is smaller than the uncertainty associated with the green horizon. So we're actually learning about what we know and what we don't know now by making all of these different models. We can also do that on a local scale, because we can say, okay, I'm going to make a voxel model, and then I'm going to make another voxel model, and then I'm going to make 998 other voxel models. And for each voxel, I'm going to say, what is the number of different lithologies that I'm going to find in my 1,000 models? And when it's transparent, and this is the work of Mark Lindsay from the Gippsland Basin, when it's transparent, it means that he ran the model, I think in this case it was 100 times. He always got the same lithology at this voxel position here. But at these red ones, there were up to 6 different lithologies that occurred in the same voxel space. So that means that in these areas where it's yellow and red, there's much more uncertainty than there is in these areas where it's transparent. And again, that tells us something about what we know and what we don't know, but now it's on a much more local scale. It tells us that this area is very under-constrained by the existing data sets. Small perturbations in the existing data result in large differences in our predicted lithology. Another way of looking at this is at the global scale, and global meaning the entire model. where let's imagine that what we actually care about is the volume of some particular unit. It might be a pluton, or it might be a dike. We want to know what's the volume of this particular lithology. Or it might be what's the depth of this particular lithology, or it could be how deformed is it, how complexly deformed is it, or any other number of parameters that we care about. The model is telling us all sorts of things, but as geologists there might be some particular aspect of the problem that really matters to us in terms of our understanding of the area. And so we can describe all of our 1,000 models in terms of things that we care about, rather than just having billions and billions of voxels. And then we can do something like a principal component analysis, and once that's done, each of these red dots is a model. So now we've reduced all of our millions and millions of voxels down to a parameter space based on things we care about, and we can actually look at that and say, well, there's a whole bunch of models that cluster around here, and this is probably the most representative model. It's got the average properties in all of the different parameters that we care about. And interestingly, the initial model in this case was this green one here. So the initial model, in a sense, isn't the most representative model that we could produce. So our best guess model wasn't actually the best model, as it were, and that's a fairly clear demonstration of that. But it also shows that there's quite a wide variety of different possible models, all of which more or less fit our observations. I'm going to talk about topology for a bit. And topology is what I'm working on at the moment, and it matters for a number of different reasons. If we're trying to think of mineral systems, the model that you've seen several times today is that there's a source, there's a pathway, and there's a sink. And especially in the pathway stage, clearly how something gets from A to B is dependent to a large extent on the connectivity of the pathways. So the pathways, if you want to say they're faults, then sometimes they're single faults that connect all the way through up from the mantle to the surface of the Earth. But oftentimes, especially when you get into the upper crust, it's a much more complicated array of faults. And if you want to look and see whether fluid that starts at A can get to B, you have to look at the pathway, and the topology is a way of looking at that pathway. Do these faults connect? Do these lithologies connect? Because sometimes it's a porous lithology that's allowing you to transport things, and especially in oil and gas, that's often the case. One of the things, especially, I'll talk about this one of the things, especially for geophysical inversions, is that there are packages like GeoModeler, for example, and I'm not picking on GeoModeler because it's actually the one we use, but GeoModeler, you put in a three-dimensional model, and then it'll do a petrophysical inversion based on that three-dimensional model, but it won't allow you to change the topology of the model itself, because it's just a degree of freedom. They found that if they did allow to do that, the model broke up into lots of little cubes, and you lost any coherence. So they deliberately stopped the ability for the model to evolve from one topology to another. And if we play this game of producing 1,000 models, and here we've done it just using Noddy because it was the easiest to do the topological analysis for, but we have a much reduced, much simplified version of the Gippsland basin model with some unconformities, some faults, and some folding going on. And we can automatically analyze a model like that for the connectivity between different lithological volumes. And so the balls here refer to contiguous volumes of lithology. The lines, or the edges they call in topology, confusingly, represent the surfaces that divide two lithological volumes. And obviously the types of surfaces, they could be stratigraphic, they could be unconformities, they could be faults, they could be igneous intrusions. There are no intrusions in this model, so it can't be that. But this is where we end up with a diagram like this. This is called a network graph, and they're kind of fairly intuitive, because you can see that this particular volume might refer to that volume, and the connection down to this volume here might be this surface in there. So from a visual perspective they're kind of easy to get your head around, because there's a spatial relationship that you can see here The trouble is comparing two of these things is a bit of a nightmare. And there's a lot of work that's been done in molecular biology and also IT trying to compare two networks. So it can be done, but it tends to end up with a sort of global comparison. You can say this network is more like that network than that network is, but the detail is often quite hard to pull out. And so what I'm looking at more in particular at the moment are these things called adjacency matrices. And so in adjacency matrices, you list just along the top in any order you like all the different lithologies in your model. So there were 16 different rock types here. You list them all the way down here as well. It's the same 16. And if a square is colored, then it means that those two different rock types were touching each other in the 3D model. They were really neighbors. And the color of the square here tells you what sort of neighborhood relationship was. If they're separated by faults, they're separated by unconformities, there's a stratigraphic relationship. And if you do this game for 1,000 different models, this number up here is telling us that there's 100 different topologies for these 1,000 different models. So there's 100 different, if you want to think of it in fluid pathways, there's 100 different fluid pathway models, or 100 different electrical conductivity models that come out of our 1,000 different models. So there's a huge variety of possibilities. So when you have one model, you throw everything at it and you hope for the best. When you have 1,000 models, you actually get to test things. Because if I put in one drill hole into this and I establish that I've got two different rock types that are adjacent to each other in the drill hole, I can then throw out of my 1,000 models all of the models that didn't predict that. So one drill hole can suddenly throw away great numbers of models. So it's really powerful in terms of what you can get out. You can actually put a drill hole in that will test which of my 1,000 models are most likely to be right, or which 150 of them. Which 150 of them are most likely to be right. So drilling goes from being something where if you miss it, yes, you do learn something, but mostly you learn you're not going to get any more funding, to something where you actually get to throw away possible solutions and reduce the set that you've got left. So this is just an example of just sticking on the topology. This is cross-sections as a function of time. So we've got stratigraphy, which is then faulted with a dike going through with an unconformity over the top. And this is the network diagrams, and these are the adjacency matrices for that. And we can see that there's a significant evolution of these with time. And it might be interesting, 20 years' time, to actually say, is there something topological about our ore deposits? Is there something that's different about the big ore deposits than the little ones? We're not there yet because we can't characterize the deep behavior of the deep pathways, but some of the stuff that Mike Dent has been showing about the MT work means that maybe we will be able to do that in the future. So this is just leading into geophysical inversion, and what's wrong with this picture? This is an MT inversion, a density inversion, and a magnetic inversion from Burkina Faso and Ghana, where we do a lot of our work. And you spent hundreds of thousands to millions of dollars on the data acquisition. You've used some of the biggest computers that currently exist on the planet, and then you print out the image and you draw lines on it. Something's gone wrong in this logic. I mean, the first two, I cannot fault the logic. The third one, the reason that the third one, I mean, I draw lines like the best of them, but the reason the third one is wrong is because we've had to throw away all of the geology data that originally went into understanding these areas, and we're only applying it in a very general sense again at the end. So this is just another way of saying the same thing, is that we take all of our knowledge that we have to build a prior model for geophysics, and this is an example from southwest Ghana. It's a 3D model of the Ashanti Belt. When we calculate forward model the gravity magnetics, clearly it doesn't work because there's no way it could work because it's way too complicated. There's too much going on. So it doesn't explain the geophysical signal, so we create an inversion scheme, and this is the one I like to use, and it spits out some sort of geophysical inversion based on the prior model. You can do it without a prior model, but then, as a geologist, I kind of object to that in general. But that's a philosophical thing. But the problem with doing this process is that by passing it through my inversion machine, I've had to let go of all the geological information. You're using it in a general sense because you've provided the starting model, but by the time you get an inversion out the other end, I can no longer make predictions about the dip of a fault or whether two faults intersect. That's just asking too much of the geophysics. So at the moment, what we have is a system where the inversion schemes, when you pass over the information from the geology to the geophysics, it loses all of the inherent geological knowledge that goes with the petrophysical prior model. And that's what we need to try and keep in the future. We're not there yet. But by producing 1,000 different models instead of one, there's a number of different pathways that we can go to keeping that geological information further in the process. So one of these, for example, is that here we have our 3D voxel model of uncertainty, and we can say that where it's transparent, we always got the same petrology. Therefore, the possible range of petrophysical responses for that voxel are probably going to be quite narrowly defined. When we go to the red areas, there were 6 possible lithologies. So then, we could say that instead of saying we don't know what the density is, we could say, well, let's choose between one of these 6 densities, or well, let's choose between a probability density function based on these 6 lithologies. So that gives us a significantly improved way of doing inversion. At least that's what we'll find out soon enough. We've got a student starting soon, but hopefully it's going to look at that. Another way of doing it is by doing what we might call brute force trial and error. Let's make 1,000 geological models and let's calculate the gravity response for them. And this is the work that Ruth Murdy has been doing in the sandstone greenstone belt in the Yilgarn, where she built an initial 3D model in GeoModeler and then started to perturb the input data to simulate the uncertainty we had for that area. You end up with a whole bunch of different cross-sections of this 3D model and the 3D model itself. This is the observed gravity, and we can end up with 6 different versions of the gravity data. Once we've decided which ones are closest to the observation, we could perhaps then go into an inversion phase and pick only the ones that are closest in the first place to the final answer. Or, as somebody suggested yesterday, we could actually just put the whole thing into an inversion scheme and say, let's use the input data and the perturbation of that data as part of the entire inversion scheme. Another possibility to try and reduce the problem is to pick n members, and giving credit where it's due, I think it was Mike Dentith that put this idea into my head a couple of years ago, that if we do the PCA analysis, which we were already doing, we can pick n-member solutions as being representative of the variety of different 3-dimensional geological models we have, and then we're testing the most different models and seeing one way of looking at this and saying whichever inversion required the least work to get to the final answer might be the closest combination of geological observation and geophysical observation. The topology, for certain types of geophysical inversion or for certain types of observations, such as fluid flow for hydrogeology, the topology is quite attractive, the topological analysis is quite attractive because it results in a massive reduction in the dimensionality of the problem. Instead of having a model with maybe 100,000 voxels in it, we've got a model with maybe 30 balls and 30 joins. And if you can calculate resistivity in a system like this in essentially 0 time on a modern computer. So you could run through your 1,000 different models and say, okay, based on the resistivity measurements I've got, these ones are the ones that basically respond to first order behavior, and those are the ones that I'm going to focus on. Or if you were doing fluid flow in a hydrogeology system, you could say, these are the ones that, any system that looks like this takes 0 time to calculate. So the time goes away, and then you can pick the ones that are most like your system and expand it out again to do a full inversion. So I'm going to finish a bit early, which is unfortunately going to give me lots of time for questions. But the conclusions are that geologically constrained inversions require more than just the best guess single model of the geologist as the input. If you do that, it's asking too much of the regional geophysical data sets to produce the right answer. But by using uncertainty and topological metrics, that we can already think of 4 different ways that we can improve the geophysical inversion schemes by providing them with a more geologically insightful set of models to work with. So, thank you.
Do you have questions? Topology.
You know you love it. Yep.
Yeah.
Thanks, great talk. I presume the conclusions you're drawing in your experiences are really based on regional potential fields in the geophysics mostly. My experience is much more in airborne EM, and the approach there is quite a bit different. I mean, there is a lot of information within the airborne EM data, and people are putting geological constraints in there, trying to also use the single best guess as we start. So can you comment on that? Potential fields versus airborne EM?
Well, I mean, it's for what I mean. Well, there's several different things. One is that there's airborne, there's gravity magnetics for many places. There's airborne EM for many poaching stamps. I think it's fair to say. So it's not that you can't do it, but if it's not a universal solution yet. It may become that, but it's not there yet. The second thing is that even if you're putting in the best guess model, why would you limit yourself to one? Don't you first want to understand what the geology is telling you? Otherwise, you're not really understanding the geology, in my opinion, and in the opinion of the co-authors, if you only make one model. Because geophysicists are very comfortable with exploring parameter space. So why would a geophysicist accept the geologist's rather random exploration of parameter space and then go through all of this beautiful work in geophysics? Wouldn't you want the geologist to have done the same thing as you're doing?
Sure, but I guess in EM the results are much more data driven than
more data driven, but honestly, you never get surprises when you drill EM.
Yeah.
There was the example yesterday that was given about the Tibby belt, where there was quite a lot of EM data flown and they never found anything. So, it's got better since those days, but I honestly don't think one geophysical technique is ever going to give us all the answers, because what happens if your 2 different rocks that you want to look at aren't electrically different? You've got to use every data set.
Yeah.
To me, that's the fundamental, whatever you're doing, why would you not look at a data set, and why would you not explore the uncertainties associated with that data set? I'm not going to argue whether one data set's better than another. I think that's the wrong way to look at the whole problem. The way to look at the problem is we need to use chemistry, physics, maths, geology, because there's not really any of those things, and we need to use all of them, and we need to understand the limitations of all of them. So I actually don't accept the premise of the question that one data set is going to give you all the answers.
Yeah, I acknowledge that. I'm just saying that I guess this approach is, I can totally agree to that with that type of data, with data set that have got more information within themselves. There's different approaches being used that it's just a little bit different.
Yeah, I mean, I guess the other thing is that different types of deposit are, using EM for looking for orogenic gold, not so great.
Did Steve have a question? No.
Yeah. So what's the time frame for commercially viable solution?
How much is industry willing to give us in order for that to happen?
That's right. How long is a piece of string?
Yeah.
This is a complete restarting of 3D software systems.
I mean, we're already developing software that is a front end for GeoModeler. And what we're thinking of doing this year is making it a generalized front end so that any of the implicit schemes, meaning GoCAD Skewer, Leapfrog, GeoModeler, whatever, that you can play these games. They're basically, we don't want to touch really. I mean, we would love to get the source code and make the geology bit better, but that's another whole problem that's not necessarily relevant to this audience. But what we do think we're going to do is we're going to put just like you do in finite element analysis, you have a preprocessor, you have a black box that you press the button and it gives you an answer, and then you have post-processor. And what we're probably going to focus on is the preprocessor and the post-processor, so we can make 1,000 models and we can analyze those 1,000 models, and we'll leave the 3D bit, although we do keep bugging them to say that their software is crap. They ignore us, by the way.
Is there a short-term answer in terms of taking existing software and providing visualization?
Well, that's what we're doing at the moment. I mean, we're talking. This year we've got a postdoc we've still got to work out the details of what he does. But one of the things we'd like him to do is build a general preprocessor that allows you to take your starting data and generate 1,000 models from it. And then the next step is to take 1,000 models and to take what we've learned from it. And I really am a big believer that every data set is important, and we're doing it in this 3D geology space, but I think the logic applies to everything. And geophysicists have been doing this forever with geophysical inversions, but oil and gas has been doing it forever with petrophysical inversions as well. It's just not really been applied to geology that much.
There is and I've talked to Mark about this a couple of times. I guess I'd call it, and you can correct me because you know the right vernacular, another class of modeling that the oil industry has been working on, largely under a project that I'm aware of called SEAM. And it's basically creating real-world models of oil fields that are populated, as I think Graham Beggs had thought that they lack the granularity, but in fact these models are so detailed. I've seen actual borehole geophysical results come out of these synthetic models that looks like real data. These are terabyte-sized models. And one of the reasons the oil industry does this is because they are very much involved in 4D monitoring of systems. And the problem is a real oil field is messy, and it's a one direction. Once you start pumping out oil and pumping water in, it changes. And if they've got an improvement to technology, they can't just rush out to the North Sea or rush out to the Gulf of Mexico. It's very expensive. And plus the thing that they're testing has changed. But the model can be set back in time artificially, or it can be moved forward. And it's something which Iago will be out at CET tomorrow, and he's the director of SEAM. We've had a few discussions with some of the mining community, and we're sort of thinking, well, from a training perspective, and maybe from a modeling, can we do, if Graham at Adelaide wants to try out a new MT technique, sure, he can go to the field and it's always fun, but you could run 1,000 experiments on a synthetic model. You could run 1 or 2 in the real world, not really know what's underneath you, whereas in the model you know exactly what's underneath you. That's one of the restrictions that we probably have, is we don't have the richness of the physical property data that the oil industry does, and that is not something that I think we're ever going to surmount. We're going to have to go around that barrier. I don't think we can take the physical property story head on. I mean, I've been in too many rooms for too many decades listening to this is important and seeing it's not getting done. And I think we're going to have to be more inventive. I was thinking, Mike, on your talk, can we work with physical properties as gradients as opposed to absolute value? Can we try and map changes like we do in magnetic tilt information and say we're never going to know what the absolute resistivities are, but can we map gradients within the data? Anyways, you want to, I've done my sales pitch.
No, I mean, I know 3 projects at the moment that would all use that sort of model for completely different end uses. And so, again, it's, you know, when would it happen? When somebody funds it. But it is actually a technically very challenging problem, and it's the same problem I alluded to at the beginning, is that it's a multi-scale problem. It's, you know, how do you go from building these sort of models to predicting the susceptibility at the 1 meter interval? Because you're going through 2 or 3 orders of magnitude of scale, and the processes that produce this model are a different set of processes than those that produce the susceptibility variations at the meter scale. And so you have to go up and down scales, and that's something that a great number of scientists in all sorts of fields are struggling with. It's non-trivial.
One, you know, you sometimes say, well, these models are just for the benefit of the people who create them. But last year, a guy from Exxon in Houston came up who had been using these models quite a bit inside his company. And he was talking about marine acquisition. And he said, we've actually found through modeling that the whole industry is doing it wrong. That you don't do the towed streamer. He says, you're far better off putting the sensors on the ocean floor. But the CGGs and the Halliburtons and the Schlumbergers have got too much invested in all those vessels to change. He says there's a few groups, the military and some academics, scripts, they have drones that can actually put seismic sensors on the ocean floor. He says that's the place we need. That came out of the modeling study. So he said that paradigm, it's going to take quite a while because these companies have got billions of dollars worth of these vessels. He says, you know, we're going to improve seismic acquisition. It's going to come out of a major step change in the acquisition approach. But the concepts came out of this modeling. And I'm surprised that Halliburton hadn't taken him out or something. It wouldn't be the message most people would want to hear. But anyways, it's not just an airy-fairy result. It was actually a pretty interesting one from the point of view of what you need to do in that business to make a major change. So anyways, Ben Mark, thank you.